Hello, and welcome to the next session in my webinar series on C++ Standard Template Library by example. Today, we're going to wrap up our coverage of non-mutating algorithms, focusing on algorithms that search within a range. So let's go ahead and take a look at the code we'll be inspecting, and then we'll jump right into it. So I'll start by sharing my screen, and you can see that we're going to be focusing today on my C++ STL-S10 10.7 folder, and we'll see there are 4 projects under here, 10.7a through 10.7b. So let's go ahead and take a look at the actual source code. There's a number of algorithms in STL that will search for elements in an integer range, and these algorithms include search, which looks for the first range, in a first range for the occurrence of a second range, possibly using a binary predicate or a value. Search n, that looks in a range for the occurrence of n items that are equal to a value, again, possibly using a binary predicate. Something called adjacent find, which could either go under the find or the search algorithms. I'm putting it here because it basically acts as kind of a lobotomized search n, and it looks in a first range for a pair of values that are adjacent to each other that have the same equal value or compare equal with a binary predicate. Then, of course, there's binary search that searches in a sorted range to find an item, and it'll do that in linear time. And then there's also another algorithm that's called lower bound, which is similar to binary search, except that it returns an iterator to the item that's found, whereas binary search just returns true or false. It's not really all that useful, quite frankly. So lower bound is a more useful method if you're trying to find the item with binary search and do something with it once you found it. Okay, so let's take a look at the first example. This example is going to demonstrate how to use the STL search algorithm. And we're going to give it a couple of strings for input. One string is going to be the famous phrase, "Now is the time for all good people to come to the aid of their party." And the other phrase is a famous lyric from a song by Yes that says, "I've seen all good people turn their heads each day, so satisfied I'm on my way." And then we're going to be searching for the subsequence, all good people, which of course miraculously appears in both of these quotes. So we're going to go ahead and start searching using search for sequence or search for subsequence, which is a helper method I defined. And we're going to use that to search the vector. And then we're going to go ahead and use search for subsequence to search the list of strings. So we have a vector of strings and a list of strings. And you'll see that in both cases, we're going to be searching we're going to use the subsequence to be an array of strings. So we're showing how you can write generic code that can be used with vectors, lists, and also arrays. So let's go down here and take a look at search for subsequence. And you can see search for subsequence takes a pair of input iterators, input iterator 1 and input iterator 2, and then it takes the ranges within the first input iterator and the second input iterator to search for. We write out the name of the function using a little convenience macro that's provided for us, and then we go ahead and we use the search algorithm. And if we find a match, if it turns out that the subsequence in first 2 through last 2 is found in the original range, first 1 through last 1, then we'll get an iterator, and we'll go ahead and say where the match occurred. Otherwise, it didn't occur. So let's go ahead and run the code and see what it does. And you can see here that when we looked this up, we found the subsequence, all good people, appears in the first vector starting at index 5, which is indeed where it starts out. All good people shows up there starting at index 5 because we're counting from 0, of course. And then in the second list, it turns out that all good people shows up starting at index location 2, where you see all good people starting here. So this did indeed work, and it shows you how you can search for subsequences. And here I'm using a list of strings or a vector of strings, but you could use other types as well. Okay, so that's the search algorithm. Now let's go ahead and take a look at a similarly named algorithm called search n. And here we're going to have the same basic input. We're going to have our "now is the time for all good people" phrase as a vector of strings, and I've seen all good people phrase as a list of strings. And once again, we're going to have an array that's going to look for all good people. And what we're going to do here, just to kind of make this really interesting, is we're going to call a helper method we wrote, which is named search n for value. And what we're going to do here is we're going to be looking for anywhere in these ranges, either the list or the vector, where we'll find two consecutive occurrences where words start with the letter T, in the case for the vector version, L1, which is this guy up here, L1. And then in the case of L2, we're going to look for any place where we see two consecutive words that start with the letters S, or the letter S, two words that start with S. So this is kind of funky and kind of cool. So let's see how we're actually going to do this. I'll show you the search n for value helper method in a second, but first I'm going to show you that we're going to be passing in a binary predicate. And you can see here the binary predicate takes a const string ref S and a const string ref V, where V and S are the values that we're looking for, and they need to be adjacent. And we're checking to see if the first letter of S equals the letter V, where V is actually the value that's passed in here. And so it's going to go through and it's going to try to find two adjacent elements that have that condition, that predicate met. And down here, we're going to do the same thing, except this time we're going to pass in the letter S, and we're going to check to see if there's two adjacent values, and here's 2, the size of 2, that have the letter S as their first character. This is the actual search n for value generic algorithm that I wrote to do this. You can see here that we have a forward iterator, a size, which is a value, type name T, and then a binary predicate. And so down here, we're going to have the range from beginning to end. We're going to have how many things we want to be consecutive. That's what size is. We're going to have the value that we're looking for, and then we're going to have the binary predicate. So let's take a look at what our code looks like. What we're going to do here is we're going to start at the beginning, and while we haven't reached the end, we're going to call search n, looking for initially the beginning to the end, trying to find matches of, in this case, 2 elements that have the value, in this case, the string T or the string S. And we want to just compare the first characters to see whether they're equal. And what we'll get back will be an iterator. And if the iterator doesn't equal the end, in other words, we actually got a match, then what we're going to do is we're going to print out the value that matched and where it matched. And then we're going to set temp, which is this value that's used to restart the search, skipping over what we've looked at so far. We're going to increment temp by iter plus plus. So we're going to increment the iter by 1 and then start the search again. Now, this will keep going either until we've reached the end or we keep finding things. And if we have reached this point where we don't get a match and temp equals first, that means we didn't find anything. So we print out the value of the output saying consecutive values were not present. Okay, so let's go ahead and run this program and you'll see what we'll get. It's kind of cool and kind of fun. So here you're going to see that we found 2 values of T at position 2 in our initial string, our vector of strings. So here it is, the and time contain T's and they're adjacent to each other. So they have the value of 2. And then you can also see that we found, again, T appearing later. So 2 and the also appear, and that appears at position 10. So we got the match as we expect there. And then down here in the other lyric from the song, we find that S appears in 2 consecutive elements where the S is the first character with so and satisfied. So those were examples of where we got the matches. So this is demonstrating how search n works. And you can see, you can either do the full comparisons or you can pick and choose the elements of the values you're searching on, as I do here. Okay, now let's go ahead and take a look at yet another example. And this one's kind of fun. This is basically kind of a variant of what we just looked at, except rather than using search n, we're going to use another STL algorithm called adjacent find. And as I mentioned before, you can either look at this as one of the find family of algorithms like find, find if not, and so on, or you can look at it as kind of a search. And what it does, as we'll see in a second, is it's kind of a stripped down search n, where it looks for two adjacent elements that compare equal. But unlike search n, you can't give it more than two. You can only look for two that are adjacent, that have the same matching value. So again, we'll give the same input. Now is the time, and I've seen all good people. We'll search for all good people again, except this time we're going to use adjacent find for pred, which is this helper method I wrote to use adjacent find. And in this case, we simply give it the container that we want to search for. We're not dealing with iterators here, just to mix it up a bit. So we give it the container. So this will work for lists or strings, or lists or decks or vectors and so on. And then we also give it a binary predicate, which is just like the one we looked at in our search n version of this, where we're just going to look for the characters that have the same letter that happen to be adjacent to each other. And then we do the same thing, except this time we pass in the list as opposed to the vector. So let's go ahead and look at adjacent find for pred. And you can see in this case, it's a template function that's parameterized by the type of the container. So it'll take any sequential container, as well as the binary predicate. So down here, we have code very much like we did for search n, but it's just a little different because we're not using search n, we're using adjacent find. So we start at the beginning of the container, and we keep going till we reach the end of the container. And what we do is we do adjacent find, starting initially at the very beginning, and we look through the entire container using the predicate, which will determine if two adjacent elements have the same value, because their predicate will return that they have the same value, and they'll have the same value if they have the first letter. And again, much like we did for search n, if we don't run off the end of the container, we'll print out that we found two values at iter star iter sub 0. So we're going to index and print out just that character, are found at the position that's designated by the distance from the beginning of the container to the iterator where it ended up getting the match. And that distance method is basically STL's way of doing pointer arithmetic for things that may not actually be pointers, but maybe iterators instead. And again, if we don't get a match, we'll print out we didn't find the values. So let's go ahead and run this code and see what we get as a result. We got some interesting results here. We find that we're going to find two values of t at position 2, and that's the same thing we found before. That's the time. And then we also find two values of t at position 10, and that's to the. And then down here in list of strings L2, we find that there's also two adjacent values. You can see that t turns up in position 5 with turn there, and we find s in so satisfied. So this is, it could be like an alliteration finder, I guess. But basically what this is doing is finding matches that are adjacent to each other. And once again, we're showing the power of STL to be able to write generic code, be able to plug in predicates that do very interesting and somewhat non-conventional things by just indexing into the appropriate pieces of the search keys we're looking for to get a very, very fine-grained match. We're now going to return our attention to the last of our non-mutating algorithms that we'll be covering. And this will cover binary search, and it will also cover lower bound, which we're going to wrap up in a little helper method called binary find to compare and contrast it with binary search. So let's take a look at the example. As before, we're going to have the quote, "Now is the time for all good people," except this time we're going to put it in a string array as opposed to a vector. We had a vector string before, now it's an array of string. And then we're going to have another string, which is going to be the words we're going to search for in our quote, which are going to be the words "to find all good people." And the first thing we're going to do here is we're going to sort the string array. And we do this by using some convenience methods that are provided by STL that will let STL wrap a built-in array so that you can get the beginning and then the end, and those can be used as an iterator range. And that just handles all the gobbledygook under the hood to figure out how far off the last element is from the first element. So once we sort that range, then string A array will be sorted. It'll be in sorted order. The next thing we're going to do is we're going to use the binary search algorithm to start searching through the other string, the string of search words, to find all good people. And as you can see here, if we find a hit by using binary search, then we're going to go ahead and print out that we found the word. Otherwise, we're going to print out we did not find the word. Now, the tricky part about binary search is it's a Boolean. It just returns a Boolean, and it doesn't give us the location where the element was actually found. And that, quite frankly, is rather annoying. So as a result, we're going to show another example here using my little helper method called binary find. And that's going to use the lower bound method that's part of STL in order to go ahead and do essentially a binary search that returns an iterator to the item if it was found. So down here, we're going to make ourselves a vector of string, which will just be a copy of the range of the integer A. And then we're going to go ahead and print out the contents of that vector. And of course, the contents will be sorted because we sorted that array earlier. And when we print this out, it's going to tell us the index location of every one of the elements. And that'll make it easy to tell when we do the binary find whether it worked or not. So then the next thing we do is we have another range-based for loop where we go through the list of words we're searching for. And for each word, we go ahead and do a binary find on it. We'll look at the binary find code in a second. Just imagine for a moment it does binary search, but it returns an iterator if it gets a hit. And in this case, just for fun, we're going to give it a const iterator at the begin and a const iterator for the end, and then the word we're going to go search for. So if we get a match, if we don't have the iterator we find be the end iterator, then we're going to go ahead and say we found the word at index, and then we're going to say what the index is, and we can get the index by using the distance algorithm, which figures out how far away the iterator is from the beginning of that vector. So that'll just tell us the index. We can match that up against the printout we have here. Otherwise, we don't get a hit. So let's go ahead and take a quick look at binary find. That's defined up here. You can see it goes ahead and is going to be, by default, it's going to use the compare algorithm, and it's going to make the compare algorithm be less. And so it'll compare them in lexical order for less. So it assumes the range is sorted in ascending order. The lower bound algorithm gets called here, and it'll go ahead and search for the value using the comparison function, which in this case is less. And if we get back something that is not equal to last, then we go ahead and we check to see whether or not the value we're searched for equals the one we found. And if it doesn't compare less, then we say that we got a hit. Otherwise, we say, sorry, we didn't get it. We didn't actually find what we were looking for. So that's just a little extra sanity check to guard against some weird cases where you get matches that aren't really matches. So let's go ahead and run the code. You can see here, we get the output, and it basically says we searched for 2. Here, by the way, is what we're searching for. We're searching for to find all good people in this quote. It won't find, it'll find 2, it'll find all, it'll find good, it'll find people. So those all get matched. But unfortunately, the binary search algorithm doesn't tell us where they were found. So we then go ahead and print out the contents of the sorted vector that we made. And now we search using the binary find convenience method, the one that's down here. And in this case, it still won't find, of course, but it'll find all the other words we're searching for, and it'll tell us where they were found. So for example, 2 is found at index 14, as you can see down here. And all is found at index 1. And good is found at index 4. And people is found at index 9, and so on and so forth. So just kind of showing you that this actually works. So this illustrates the algorithms that we wanted to talk about over the past couple of days that focus on non-mutating behavior. In other words, they don't actually change the contents of the containers that they're searching over, or looking for maxes or mins over, or finding, or other things that we've talked about. So what we're going to do next is we're going to start discussing various mutating algorithms. But before that, we may actually take a little diversion and show a fun case study that exercises some interesting STL features and also shows off again the adjacent find algorithm. So I think we'll probably talk about that tomorrow, and that one's fun. It's basically a calendar scheduling or meeting scheduling conflict detector tool, and I think you'll enjoy it. It's a good example of how powerful STL is and how you can use it for all kinds of interesting use cases. Well, thanks very much again for joining, and please feel free to like and subscribe, and I look forward to talking to you again soon.